Hello and welcome to this Bio43 pre-lab video. Today we're going to talk about sources of error in experiments, what summary statistics are, and how to calculate them. These are important parts of thoughtfully designing experiments and using quantitative reasoning to statistically analyze experimental results. Right now, I'm in the Intro Bio lab for the first of our experiments. I will be sliding a quarter down the textbook and measuring how far it travels. Don't worry, later experiments do get more exciting than this. So I put the quarter at the top of the book, let it go, and I see it's traveled a distance of 16.3 centimeters. Now let me do the exact same thing, and this time I get a value of 20.4 centimeters. But if I set things up identically, shouldn't the results be exactly the same? Well, yes, but the problem is that it's impossible to truly repeat something, even for a procedure as simple as this.
The change. Why? Because tiny variations...
As much as I try to perfectly repeat the procedure, sources of error will cause the measurements to turn out differently. Errors can arise from a variety of different sources. The tools we use could be inaccurate. Aspects of the environment can change. The methods we use could be flawed. Or sometimes we just make mistakes. When faced with a strange or unexpected result, students tend to assume it was something they did and jump straight to human error as a source. But I want you to take the time to really think about the other sources of error that could be affecting your experiments. If we keep repeating the experiment and measuring the distance traveled, as long as the errors are random, just due to chance variations, we begin to see a pattern emerge. Some measurements occur more frequently than others. And if we were to plot the frequency of each potential measurement, we would see a shape like this, a normal distribution. No matter what you're measuring, as long as the sources of error are random, you'll see a curve like this. Curves will vary in specifics. Lesser error leads to narrower curves, and greater error leads to wider curves. But the curves can all be summarized with two parameters, one that describes its center and one that describes its width. Now you'll only ever get a curve this nice if you spent an infinite amount of time repeating the experiment and got values for every potential way a quarter could slide down that book. That's of course impossible, but we can reasonably estimate the center and width of the curve by doing this a small number of times. Just like if you wanted to know the height distribution of Americans, you couldn't measure the height of every American, but if you measure a random sampling of Americans, you can get a reasonably accurate number. Information about populations can be estimated by measuring samples. And the larger your sample is, the more likely it is to reflect the full population. Let's try calculating our parameters with Excel. I'll be doing my demonstrations in the Excel 2016 desktop app. The formulas I show you should work in any version of Excel, but when it comes to graphing, the online version lacks important functions, so you should make sure to use the desktop app for that. Now I've slid the quarter down the book 5 times and got the values listed here. Since I repeated the test 5 times, the sample size, or n value, is 5. In Excel, you can get the sample size with the formula equals, count, open parentheses, select the data, close parentheses, which is really more useful for data sets that aren't this easy to count on your own. To estimate the center of the data, we often use the mean, the sum of the data values divided by the number of values we measured. In Excel, this is simply done by typing equals, average, open parentheses, select the relevant data points, close parentheses. The width or variation of the data is often represented by the standard deviation, a measurement of the degree to which the individual values in the dataset differ from the mean. You don't need to worry about the equation to calculate it in this class. You can again just use a simple Excel formula. Equals stdev dot s, open parentheses, select the data, close parentheses. However, this is just information about our sample. We want to know about the population that this sample is meant to represent. And it's unlikely that the mean of the sample will be identical to the mean of the population. But we can use the mean and variation of the sample to gain insight into that population mean. One common measurement is the standard error, which is the standard deviation divided by the square root of the number of data points. However, this is a bit tricky to understand conceptually, so we prefer to use confidence intervals in this course. Confidence intervals provide a range over which the mean of the population is likely to occur. First, we choose a significance level, or alpha. We'll talk more about this later, but it's essentially the proportion of the time we're going to wrongly claim the data supports our hypothesis. Obviously, we'd like that never to happen, but the lower we set the alpha, the greater the chance we wrongly claim the data does not support the hypothesis. Most fields of biology have settled on an alpha of 0.05 or 5% as a good balance. But keep in mind that 1 out of every 20 experiments that uses that threshold and claims their hypothesis is supported will be incorrect. Again, this is why you never want to say anything is proven by the results of a single experiment. Our confidence level is 1 minus our alpha, so we will be using 95% confidence intervals. We will be 95% confident that the mean of the population lies within the range we calculate. The Excel formula for the 95% confidence interval is the most complicated one we use in this course. It's equals confidence dot t, open parentheses, our alpha value, 0.05, comma, the formula for standard deviation, comma, the formula for the sample size, close parentheses. Though if you've already calculated the standard deviation sample size, as we've done here, you can save some time. Instead of rewriting those formulas, you can just select the cells that contain the appropriate values. Now the mean of the sample, plus or minus the 95% confidence interval, is the range in which we are 95% confident the population mean occurs. So with a mean of 17.0 centimeters and 95% confidence interval of 2.6 centimeters, we can be 95% confident that the mean of the population falls between 14.4 and 19.6 centimeters. One important thing to note about the 95% confidence interval is that it decreases as the sample size increases. In other words, if we increase our sample size, we can narrow down our estimate of the range for the population mean. The sample size, mean, and 95% confidence interval are key summary statistics for data like this. When submitting a report, you don't have the space to provide all the measurements you collected. But these 3 values provide a good summary of the data. The mean and 95% confidence interval are best depicted visually, with a bar graph and error bars. But that's for another video. For now, I want you to repeat the quarter sliding experiment as closely as possible to what I've done here and calculate the summary statistics for your data. When you do this yourself, you may get radically different values from mine, more than you'd expect from random fluctuations. This could be the result of systematic error. Systematic errors cause measurements to be consistently off from their actual values. Imagine, for instance, a thermometer that consistently measures 1 degree higher than the actual temperature. Like random errors, systematic errors can be the result of instruments, the environment, procedural problems, or human mistakes. But random error only affects the variation in your data. It can cause your 95% confidence interval to be wider than it otherwise would be, while systematic error could cause your values to be off entirely. The population mean will fall outside of the 95% confidence interval far more than 5% of the time. When you perform this experiment yourself, think about the sources of random and systematic error at work. For each source of error you identify, think about if it's instrumental, environmental, procedural, or human. That does it for this video. I hope you have a good understanding of the types of errors and can use this knowledge to design experiments that minimize sources of error as best you can. While error can never be completely eliminated, we can always find ways to identify sources and minimize their impact. With our discussion of summary statistics, we have just begun our journey on statistical analysis, and there will be much more to come. See you next time!